Welcome, ladies and gentlemen, to the first lesson of distance learning. Today we will be rolling out the introduction to the Taylor and the Maclaurin series. And this is basically the culmination of all of our sequences and series. Like, the reason why we were learning all of the sequences and series is so that we could eventually apply it to this idea. Now, if you need to pause for a second to write this in your notes, go for it. It basically tells us here the Taylor and Maclaurin series uses a polynomial to represent a non-polynomial function. And I already know what you're thinking. Why would we ever need or want to do such a crazy thing like using a polynomial this way? Well, there's some advantages to using a representation of a Taylor and a Maclaurin series using a polynomial to represent a non-polynomial function. So I put them down here, so paste them. The indent function doesn't work here, so I'll just make this an indent right here. To summarize, polynomials are super easy to work with. And it's because they have an infinite domain, and they're easy to integrate and derive, and they're really easy to find values by plugging stuff in. Unlike, like an e to the x, and I know e to the x is super easy to derive and integrate, but plugging stuff in and finding values is a little harder, especially if I wanted you to find like a value without using a calculator or something like that. But yeah, so the advantages of using this are pretty easy. And so, how does this work? Let's talk about, let's use a function here to represent as a polynomial using a non-polynomial function. So the example that I'm going to use here, we'll begin with example 1, and it's going to be f of x is equal to 1 over 1 minus x. Now, obviously, this is a non-polynomial function. It's a rational function. And so let's see what happens if I try to use a polynomial to represent this. Well, how do I do that? Well, on the right side here, I'm going to do it in a different color here. I'm going to have my regular function, and on the right side, I'm going to have my polynomial function. Well, a polynomial function is best represented as the most basic polynomial would look like this. It would be a, some constant, plus bx, some linear term, plus cx squared, plus dx cubed, plus ex to the fourth, plus fx to the fifth, and I think you can kind of understand where that pattern is going to go. So what I'm going to do is I'm going to derive both of these functions side by side. And then, similar to a partial fractions kind of way, I'm going to solve using some association. So before I derive, I'm going to make him a little bit easier. Because there's a constant up top, I'd rather not delve into the whole chain rule business. I'll call him 1 minus x to the negative 1. And again, I'm just going to derive these guys side by side. I'll just take care of the f's first. So f prime of x will be negative 1 times 1 minus x to the negative 2 times negative 1 for chain rule. So I'm going to make that equal to, looks like 1 times 1 minus x to the negative 2. And then f prime of x, f double prime of x will then become negative 2, and then 1 minus x to the negative 3 times negative 1 for chain rule again. So that's going to get me, looks like 2, and then 1 minus x to the negative 3. And I'm actually going to be taking several derivatives here, so if you are faster than me and you feel like you can fast forward. And I'm actually going to be taking several derivatives here. Now, I would not recommend you fast forward because I'm not going to call this negative 6. Instead, I'm going to call him negative 3 times 2, and then 1 minus x to the negative 4 times negative 1 for chain rule, giving me 3 times 2, and then 1 minus x to the negative 4. And then my last derivative here will be the fourth derivative, and it's going to be, looks like negative 4 times 3 times 2, 1 minus x to the negative 5 times negative 1, giving me 4 times 3 times 2, and then 1 minus x to the negative 5. Okay, so now that I've derived the actual function, let's take a look at what the polynomial would have derived into. So the polynomial here, p prime of x. Well, remember, all the letters of the alphabet, except for x in this case, are constant. So when I derive this guy, the a is going to go away, giving me b plus 2cx plus 3dx squared plus 4ex cubed plus 5fx to the fourth. And again, I'm going to try and keep them as lined up as I can because there's going to be some association that happens here. So p double prime of x is going to be, the b is going to go away now, so I'll end up with 2c plus 3 times 2 dx plus 4 times 3 ex squared plus 5 times 4 fx cubed. So in the same way how I didn't simplify my multiplications on the left side, I'm not going to do the same thing on the right side. I'm not going to simplify my multiplications. And I think some of you guys might be seeing why I'm not doing it, but if you don't, it's not a big deal. We will tell that explicitly in just a second here. This 2c is going to go away. He's a constant. This is going to become 3 times 2 times d plus 4 times 3 times 2 ex plus, I think I'm going to scroll over a little bit to the right here, 5 times 4 times 3 times fx squared. And then finally, my fourth derivative of my polynomial will be, this guy's gone. I end up with 4 times 3 times 2e plus 5 times 4 times 3 times 2 fx. And of course, down the chain, this thing would just keep on going, and all of these guys would just keep on going also. And so, okay, let's talk about why I did not decide to multiply everything out. Well, from here, if I change everything to red, if I change everything to ketchup here, it's easiest if I look at the fourth derivative first. If you look at 4 times 3 times 2, he's technically 4 times 3 times 2 times 1. In other words, I could rewrite him as 4 factorial 1 minus x to the negative fifth. This 3 here is really 3 factorial. He's really 3 times 2 times 1, so I can call him 3 factorial 1 minus x to the negative fourth. This 2 here is really 2 factorial 1 minus x to the negative 3. Now, 2 factorial is 2, so we're not going to worry about him, but just to keep things as clear as possible. And this is technically 1 factorial and then 1 minus x to the negative 2. Well, let's go and do the same thing on our polynomial here. Well, from here, our p prime, I can call him 4 factorial e plus 5 factorial fx. And the things that are down the chain here are not going to be factorialized, at least not yet. By the time I hit my 5th and 6th and 7th derivatives, those terms down the chain will start becoming factorialized. But for now, these are the only terms that are becoming factorialized, and that should be enough for us to establish a pattern here. So again, this would be 3 factorial d, and this would be 4 factorial ex, plus, again, not factorialized. He would actually just stay the same. And I think we're going to start seeing a pattern here. 2 factorial c plus 3 factorial dx plus dot, 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 dot. And I think we're starting to see a pattern here. Well, if you don't see the pattern, it's not a big deal. If you see the 2 factorial here, he kind of corresponds with this 2 factorial. This 3 factorial corresponds with this 3 factorial, and so on and so forth. So how does this help me build my Maclaurin series? Well, let's define what a Maclaurin series is versus a Taylor series before we get started. The Maclaurin series uses a polynomial to represent a non-polynomial function centered at x equals 0. It is specifically at x equals 0. Okay? So what I'm going to do is I'm going to now use these pieces of information here, my f's and my p's, and I'm going to just let x become 0 and see what happens. To that end, I'm going to use some association to match my polynomials to my non-polynomials. I'm going to say that f of 0 will be equal to p of 0. F prime of 0 will be equal to p prime of 0. F double prime of 0 will be equal to p double prime of 0. F triple prime of 0 is equal to p triple prime of 0. And I know down the chain I'm going to get the fourth power, but or the fourth derivative. I'm going to reserve that so I don't have to keep scrolling right and left. But I think we're going to hopefully see what happens here. What happens when I let x become 0? Well, remember, this is f of x right here, the original function. If I let x become 0, well, f of 0 is 1. And what is the corresponding value here on the p side? P of 0, well, all of these things with the x's are going to end up going away, and all I'm left with is a. If I do the same thing for p prime and f prime, if I let f prime of 0 happen, I get 1 again. If I let p prime of 0 happen, I get 1 equals b. And if you want to pause and just kind of beat me to it, you'll see that 1 equals c, 1 equals d, and even down the chain here, if I do my fourth derivative here, I'll get f fourth derivative equaling the fourth derivative of p. You'll get 1 equaling e. So how does this help me represent a polynomial? Well, remember, the original base polynomial is this expression right here. It's this. It's all of this stuff here. And so what I get is instead of a plus bx plus c x squared plus d, I have all the values for a and all those things. So I can then say that p of x is equal to, instead of a, I got 1. Instead of bx, I have 1x. So I have x. Plus, instead of cx squared, I have 1x squared plus x cubed plus x to the fourth plus x to the fifth plus dot dot dot. So this is my representation right here. Now, I am going to pause the video for a second. If you need to pause so that you can copy this down, go for it. I need to make some board space, so give me a second. I'll be back with you in a flash. Alright, this is where we left off in the problem here. We have our polynomial representation of y f of x is equal to 1 over 1 minus x. And so if you look at this polynomial right here, there should be something that stands out to you. Like, you know, it's a summation, right? So it's going to be a series. And so what type of series is this going to be? And it's not totally obvious, but if you look at the terms here, they seem to be growing at a pretty constant rate here. It seems like to get from one term to the next, I'm multiplying by x every single time. And if I'm multiplying by a constant amount, we can conclude that this thing is geometric in nature. And these dot dot dots here mean that what I'm doing is I'm going to take this all the way to infinity. And if I wanted to sum up this entire series here to infinity on an infinite geometric series, I would need to use the following formula. S is equal to 1 over 1 minus r. In this case, r is equal to x because I am multiplying by x every single time to get to the next term. So what this ends up becoming, and I think you might see this, is that s would be 1 over 1 minus x. And we are back to where we started. This polynomial is a representation of this function. Now, this polynomial here, or not this geometric series here, will only converge under a certain condition, and that would have to be that the absolute value of r is less than 1. In the case of this one, the absolute value of x would have to be less than 1 for s to converge. Now, what is the meaning of this? At this point, we don't really need to be concerned about it, but let me show you what this means. I'm going to throw down the function 1 over 1 minus x. Pretty basic rational function. We've got this down. Now again, I want to draw your attention back. X, the absolute value of x has to be less than 1 in order for s to converge. In other words, x has to be in between -1 and 1 for s to converge. Okay? So what I'm going to do is I'm going to go ahead and throw down a few terms into my f2. So Okay, here are the first few terms, and check this out. If I hit enter, notice how this graph right here models that function right here. Now, again, I also want you to notice that nothing is being modeled on the outside here. Well, I'm going to go and adjust my window real quick. And instead of x-min from -10 to 10, I'll call it from -1 to 1, which is our convergence area. You see how in between -1 and 1 we're basically on top of the function almost perfectly? This is what is known as an interval of convergence. And we will talk more about the interval of convergence in a later episode. But for now, that is representing Taylor and Maclaurin series for now. I'm going to go and stop the video here because we're running high on time, and I will do examples in another video. So I will see you in a little bit.